Hi everyone. I hope this will be the first lecture for quantum mechanics, which will just be a very short lecture. Um, this lecture will mostly be correlating to the difference between the physics in classical point of view and physics in quantum point of view. And so we're going to do a little bit of comparison between the classical mechanics and the quantum mechanics. Now, obviously, the classical mechanics playlist that I have, there is the different one, but obviously the rule and the regulations and whether how the particles behave, how objects behave, they're completely the exact same thing. They have no, you know, differences. I meant about classical mechanics, not classical or quantum. So the big difference, like the big question that people ask is, what is the difference between classical and quantum mechanics? So the main, sorry, the main idea is that what is the difference between the classical point of view and the quantum point of view? So if I were to have a particle, let's say for example, I have a scenario here, a scenario, right? An environment where anything exists. And in this case, I'm going to use the simplest example, which is particle, right? So particle exists. Now, usually when you did physics in high school or physics in first year or physics maybe in second year, maybe I'm not sure because I know that like most of like the high level physics starts from second year, but in general people who did physics, they'll say what, I know the position of where the particle exists, and from the position I can find the velocity, I can find the acceleration, I can, the keyword is find here, so I can find the acceleration, I can find the velocity, I can find force. So you can calculate F is equal to ma, and then d square v by dt, d square x by dt square, dx by dt, whatever, right? Whatever that exists in your mind, you will be able to solve that pretty much. But why are we able to solve that? Why is it that I'm saying that, oh, I'm able to calculate F is equal to ma? Why even the equation exists in the first place? Because you know the position. End of discussion. Whatever equations you compute, whatever equations you equate, whatever equations you go through, whatever equations you come up with and solve them, the core reason as to why you're able to even solve an equation is because you know where the position of the particle exists, regardless. So if I, the only thing I need is the position. Like if let's say obviously they're going to give you the velocity of the particle is moving at 9 meter per second towards the right. So in this case, you know your velocity. So you know your velocity, you know your direction. True. But there are things that you know, and it's very deterministic. So this is what you call deterministic in nature. Deterministic in nature, meaning you know, like it is set. The position of the particle or anything that represents a particle, like the force or the position or the velocity or the acceleration, it is set. Nothing changes about it. So that's classical mechanics, or that's the classical point of view that you usually read in your first year physics, in physics that what people know. But you didn't obviously. So this is what you get from the classical point of view, right? So from classical point of view, you know that everything is deterministic, nothing changes. Um, you know where the position of the particle lies, and from the position of the particle, you will be able to find the force, the velocity, the acceleration, whatever you need to equate. But one core thing to observe is that it is deterministic in nature. It is very deterministic. It's like everything is set. So if it's like saying in calculus, obviously you've done calculus, and you're trying to find one independent variable. There is only one independent variable. So you do f of x. Sometimes maybe f of x and y. You're going to do that in classical mechanics, f of x, y, and z. You are going to do that. But in general, it's like f of x. So everything is known, everything is set to you. So that's classical mechanics, right? So this is classical mechanics. Quantum mechanics is a different thing. X and y, right? In quantum mechanics, the difference is if the particle is here, doesn't mean the particle, if the particle is here, doesn't exactly mean that the particle will be there because it is probabilistic in nature. So, one core thing to observe is that quantum point of view is probabilistic in nature, meaning instead of saying, oh, this is where the particle lies, you're going to say the particle lies within this region here, within this region. So the particle will lie within that region. And in here, usually what you're given is that you're going to have set number of positions and you're going to add them. The reason you're able to add them, as in x1 plus x2 plus x3, is because it is not continuous. It is deterministic. Meaning, you get, oh shit, just 2 seconds. Okay, so, in classical point of view, you're going to do like x1 plus x2 plus x3, whatever, whatever, whatever. And eventually, what's going to happen is that when you try to add them, you can easily add them. So you can easily add whatever the position was in x1. So let's say x2, the value was, oh my bad. So x2, the value was 8, and x3, the value was 20. And so if you want to find the total position, like total position that maybe an object has covered, then you're going to say x1 plus x2 plus x3. Pretty simple. And the reason you're able to add is because each of them are deterministic in nature. So which means you know, like let's say x1 is 5, x2 is 8, x3 is 20, is given to you. Like it is set. And so you're able to add each of the set positions. In this, however, you have a range. And that range is from A to B, right? So you're not going to say calculate the so you're not going to say calculate the position of the particle from A to B, from in between A and B, in between A and B. You're not going to say that. You are not going to say that because you, first of all, you cannot calculate the position of the particle, right? Because or you must also understand one thing. We're going to do that in the later chapters, but you're going to have position and momentum, position and time. And especially this one, position and momentum, you cannot have both of them set. Like in deterministic, if you calculate the position, you can calculate momentum. Here it doesn't work like that. Here it does not work like that. So you're going to have a probability of both position and momentum. And obviously there's an equation called the Fourier equation. We're going to come to that. We're going to come to that. So you're going to encounter these equations, but if you say calculate the position of the particle in between A and B, you cannot calculate the position. Usually what you do is calculate the probability. So to rearrange, like to you know ask this question correctly, you're going to ask calculate calculate the probability of the particle existing between the region A and B. And obviously, you're going to give an equation. And unlike in the classical point of view, where it's x and y, you have x and psi. So this is not an xy graph. This is not an XY graph like you usually see. Because in quantum, you never, I mean, maybe you don't say it as a graph, you say it as a wave. Because everything is probabilistic in nature. And to determine everything being probabilistic in nature, there will be a range. Where will they set that range? They will not set that range in a graph. You must consider this quantum environment as like, okay, this is the region where the particle exists, not this is the graph that is given to me. In classical point of view, there is a graph because everything is set by points. So it's like saying if I were to differentiate between the two, this would be our classical graph. Right, so you say x and y. So you say x equals 1, y is 3, x equals 2, y is 5, like that. And then you draw a graph, right? The only reason you have a graph is because you know your values for the independent variables. You know them. So you know what x equals 1 is, you know x equals 2 is, you know what x equals 3 is, you know them. And because you know them, you're able to plot them. So if I say f of x is equal to 2x plus 1, you know your x value, now you know your y value. But in quantum, you don't have that. You have a psi and x. So this is not what you call a graph, because the only time you can call it a graph is because it is when you have the values. You don't even have the values for x. You don't have a deterministic value for x. F that. You don't even have a value for x. You can't even calculate x. What you usually calculate is a, the amplitude. We're gonna explain more on that in the next few lectures. But you usually don't calculate position, you actually calculate amplitude. And so you're going to see graphs like this or maybe like that. So if I were to consider a graph like this tells me that the particle most likely, so maybe there's a 70% chance that the particle exists within this region. Within the region A and B, the particle exists. Now, the question that you may ask, one question and then it lead to one answer. Why not 100%? Because if I say that the probability that the particle exists here is 100%, it violates the later entire quantum nature. It'll violate the entire quantum nature if they said that the probability that the particle exists within the region A and B is 100%. Because then it'll end up, yes, it'll end up like that, which there's something called wave function collapse. It happens for a very few millisecond and then goes back again, but it does happen. But in general, you do not say the probability of the particle exists within that region is 100%. This leads to my next explanation. In quantum mechanics, nothing can be zero and nothing can be one. Meaning, each of those probabilities that you see, all those will add up to one. And this is what you call normalization rule. We're going to do that. So, this is a standard statistical interpretation. So, this means that the wave function, this is what you call a wave function. The wave function of the position and time constraint must equal 1. Meaning, if I draw this graph, psi and x, each of those, because each of those are a probability. These aren't just random curves. These aren't just random graphs. These are a probability. And you see these amplitudes, you calculate them. You calculate the amplitude. I'm going to explain. I'm going to explain them. So each of those amplitudes, you add them up. And the way you add them up is by integration. Or here in this case, it'll be minus infinite, plus infinite, because the initial value is usually minus infinite, the end value is plus infinite, right? And we usually add those values, meaning we integrate them. And always, it must add up to 1. Now, if I had the same curve like that, sure, I'm saying that psi of x and t is equal to 1, only this part is 1, but you cannot have any of them 0 because nothing will be 0. No sections, no range of sections, no infinitesimal sections will ever be 0. It will always be greater than 0. So, two things to note: the infinitesimal sections, infinitesimal sections of each must be greater than 0, and the addition, the integration probability, the integration probability minus infinite plus infinite psi of x and t must always equal 1. Always, always, always must equal 1. It's like saying you're going to add up all the probabilities, right? But in a continuous format. So whether you do continuous, whether you do deterministic, everything must add up to 100%. And like 1 means 100%. And if we add, if this ends up where within the region A and B you have 100%, then it violates the quantum mechanics point of view. It just goes back to classical point of view, which again, why are you even solving for quantum mechanics then? Your course is finished, right? Your course cannot be finished that quickly, right? And yeah, so that will be a little bit of introduction. We're going to go in depth in the next few lectures. We will be beginning with, let's see, um, we're going to begin with probability. So that is where the core maths equation comes up, core summation comes up, and all that stuff. So we're going to solve all those questions one by one. And yeah, I hope you understood the first lecture, because it's going to get easier. Don't worry, it's going to get easier, right?